All right. So it is recommended that teenagers get 8 hours of sleep a night. I believe that my AP Stat students are getting less than the recommended 8 hours of sleep per night. So to test my belief, I asked you all how much sleep you got last night, and then I randomly chose 10 of you. That's what I was over here doing, random number generator. So the sample that we have are as follows: 0.2, 6, 6, 7.5, 2, 7.5, 6, 5, 9, and 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10. I want you guys to use your calculators to calculate the sample mean and the sample standard deviation. So we want to find X bar and SX. All right, what is our sample standard deviation? 5.82. So that's our sample mean. Sample standard deviation? 2.844. We are going to do a significance test. So we're going to state our hypothesis and our alternative hypothesis. Remember, null hypothesis is always going to be the null equals something. Or sorry, the mean equals something, my bad. Null hypothesis, mu equals. What do you think? Yes, sir.
True mean of 22 hours of sleep.
Let's define that. Yes, so mean is, mu is the true mean of hours of sleep for Ms. Bolt's AP Stats students. All right, so that defines mu. I think that my students are getting what? Less than 8 hours. So I'm going to let the null hypothesis be equal to 8 hours. And the alternative hypothesis would then be that the mean, mu, is what? Less than 8. Just like when we did this with proportions, we will assume that the null is true. And then we're going to see if we have convincing evidence to show that it's not true. Have convincing evidence to reject it. All right. get this one up here for us. Group this just a little bit. There we go. What conditions would need to be met? 10%, randomness, and I'm sorry, what? Normality. Okay, so we have random, we have 10%, we have normal or large counts. What did I tell you I did with all of the data to get the 10 numbers that I put up there? Used a random number generator. So 10 randomly selected students. Why do we care about randomness again? So we can generalize to population. What would the population be here? My AP Stat students. I only have one section, so you guys are the entire population here. 10% condition. We need 10 is less than or equal to 1/10 of all my AP Stat students. Do we meet that condition?
No.
No. Does that mean we just stop? So when you're doing actual statistical analysis out in the field, if you don't meet one of these conditions, there are other ways to move forward. You would have to use something else. What we are going to do for the purposes of this right here is we'll just include that in our conclusion, that we need to be cautious of our conclusion because we did not meet the 10% condition. Not met. Talk about in conclusion. And then normality, large counts. Do we know that the population is normally distributed? No, I don't have that information. Do we have central limit theorem? No, I only have 17 people in the room. No central limit theorem. So what do I have to do then to be able to show normality? Have to draw a graph. All right, so all the way from 0 to 9. And what is this a graph of here? Hours of sleep, so we're going to label it. All right, we had, where's my card? 0.2, so one over here. Have 6, 6, 7.5, 2, 7.5, 6, 5, 9, and 9. Do we have a large skew? I mean, it's skewed, but it's not like I have 12 and 0.2, right? I definitely think it's skewed. I wouldn't necessarily qualify it as a large skew just because these guys are only so high. Huge outliers here? No. So no strong skew, sorry, I'm going to call it strong skew. Or large outliers. And then you have to tell me in what. So no strong skew, no large outliers. What is this a graph of? Hours of sleep in whom? In our sample. So we have to actually state that because it's not the population that I have a graph of here. No strong skew or large outliers in the sample. This part is really important to include. Right, formulas for mean and standard deviation of the sampling distribution of X bar. So the mean of X bar is equal to the population mean, which we assumed is what? We assumed that it was 8. Mean of X bar will be equal to mu, which will be our null value. How do I find sigma of X bar? Sx, or sigma if I have it, right? Over square root of n. Since I don't have sigma, we are going to use Sx over the square root of n. This is approximately equal to. What was our sample standard deviation again? 2.844 over the square root of n, which was 10. So let's calculate that. We get about what? 0.899. Remember, this is our standard error of X bar. I want to draw a picture. Whenever we do significance testing, hypothesis testing, we need to draw a picture. What should go right in the middle of my picture? Mu, which would be not my X bar. 8, right? What was our X bar? 5.82. Which side would that be on? Left side. 5.82 or smaller, so this. Is this a normal distribution? What did we use when we did our interval testing? Did we use the z-table, the normal table? We used what? We used t. So we're not going to use n, we're going to use t. And we need to put our degrees of freedom in here. Instead of 8, when we standardize this, that's going to be 0. Instead of 5.82, we need our t-score here. So to calculate our t-score, our standardized test statistic, which is going to be our t-score, I need X bar, or my statistic, which is X bar, minus what? Minus the parameter. What is our parameter called here? Mu. Over the standard deviation. So this is going to be Sx divided by square root of n. So let's calculate this for our data. We had 5.82. That was our sample mean, minus mu, which is 8, over our standard error, which is, this one was 0.899. This is what we calculated right up here. All right, let's pop that in our calculator. What'd you get? Negative 2.42. This is our t-score. So that's what we would have right here. When we do our z-table, we can put the null mean and then our mean. But when we have a t distribution, which we have to do, why do we have to do the t distribution here again? Why not z? Because it's a mean. When we're doing means instead of proportions, we need a t table instead of a z table. Why? Why can't we just use the z table? Aren't they similar? The t distribution is more spread out. There's more variation. We've introduced more variation because we're not just estimating the mean, we're also estimating the standard deviation. So we've introduced more variation into this, which means we need a wider set. That is our t-table. All right, so scooting right down the page. Let me get my picture up here. So they reminded us here, our test statistic is a t-value or a t-score. We can use table B, but I'm going to use the calculator. I'll show you how to use table B to do this, but we're going to use our calculator. So on the calculator, TCDF. And then we need 3 pieces of information. We need a lower bound, we need an upper bound, and then we need degrees of freedom. Looking at this picture, which way did we shade it? To the left. Why did we shade to the left again? Less than. Our alternative hypothesis was that mu was less than 8. So we're going with our sample mean and smaller. So my lower bound has to be smaller than negative 2.42. I'm going to go with something really extreme here that I know is big enough. Negative 10,000. What would my upper bound be? Negative 2.82. How many degrees of freedom would we have? 9. Degrees of freedom is n minus 1. Yes.
Wouldn't there be 2.42 instead of?
Yes, I'm sorry. You're right. I wrote the wrong number down. I apologize. 2.42. Nine degrees of freedom. Thank you for correcting me. So TCDF on my calculator, that is option 6. Negative 2.42. 9 degrees of freedom. What'd you guys get? 0.019. This is our p-value. So what conclusion can we make? Did we ever establish an alpha level? What is our typical alpha level most of the time? 0.05. So at alpha equals 0.05, let's make our conclusion. What did we assume was true? Yep. Assuming the true mean amount of sleep for Ms. Bolt's AP Stats students is 8 hours there's a 0.019 probability of what? Yes. Of getting a sample mean of 5.82 hours. What'd you say? Sorry, I still couldn't hear what you said at the beginning. Oh, yes, 5.82 or less. You're right. Thank you for correcting me there. Purely by chance. So what should we do? Reject the null. Because 0.019 is less than 0.05, we reject the null. And find what? Yes. And find convincing evidence And we need to state what that alternative hypothesis is. We find convincing evidence that Ms. Bolt's AP Stats students get less than 8 hours of sleep. Is there anything we need to watch out for? Yeah, we missed our 10% condition there, so we must be cautious. Of our results. Because the 10% condition was not met. Learning the other ways that we would go about calculating the probability, the t-statistic, the p-value, if one of our conditions is not met, is kind of outside of the scope of AP statistics, which is why we're going to just kind of default to this. If you ever need to use that in the future, you would absolutely be given the tools that you would need to move forward with that. But for now, we'll just put this little cautionary at the end. All right. Important ideas for today. Same conditions that we've always had, random, 10%, and normal. 3 ways that we can show normality. Wording on this is really important. Either we are given that the population is approximately normal, and you would need to state that, and that's how we know that we have normality in our sampling distribution. N is greater than 30, and then you would have to go on to say, so, like we have central limit theorem, and that's how we know we have normality. Excuse me. Or the sample does not show a strong skew or major outliers. And it is really important there to state that it is the sample that we're looking at a graph of. When we are working with means, our standardized test statistic is T, not Z. Other than that, we calculate it exactly the same way that we would calculate a Z-score, except instead of it being a Z-score, it would be a T-score. For the p-value, it is much, much easier to use your calculator for that. TCDF, lower bound, upper bound, degrees of freedom. You can technically use table B, where we were going to find our critical value for T star when we did our interval testing. For this one, if you wanted to use table B to calculate your p-score, your p-value, you would have to try to find the closest number in the middle of the table to the t-score that you found by doing x bar minus mu over your standard error with the degrees of freedom that you have. And you would use that to find your tail probability. Calculator is going to be worlds easier than using the table. Calculator is also far more precise. hoping that a lot of what we did today felt fairly familiar. Pulling from what we did when we did significance testing for proportions, for P, and then looking at what we just did for creating intervals for means. Those two ideas kind of pulled together. We didn't talk about this yet, but what would be the name for the procedure that we just used? One sample t-test for? Mu, yes. Thank you. It would be a one sample t-test for mu. As we keep adding these procedures with the different names, I want to make sure that we know what the names are that we're using and how we know when to use them. It's really important when we're talking about the names for the tests, one sample, two sample. If it's a two sample, you're going to have subtraction in the name of the test. If it is a T interval, that's when we do our 95% confidence interval, 99% confidence interval. When we are doing significance testing, it is a test there. We're going to come back and say we either reject the null or we fail to reject the null. Once you've got this copied down, I want you guys to try the check your understanding down below. While you're doing that, I am going to go ahead and pass back the test that you guys took on Friday. Parker, did you want to see your test before you go?
Okay.
Did you want to see your test before you go? Okay. You can just leave it in the tray when you're done.
This and that, these are strong outliers.
That one has a strong outline.
So they're just the only one, because it's central point theorem.
Yes.
I was thinking that, I think next I was like, this is normal. And so
Yeah,
you get
this
there.
part looks normal. It's those guys that, without those, absolutely you would have been correct.
Okay. For this one, fair account 14%. Would you like P combined?
You're flipping a coin for each day. Is this actually a random sample?
It's an experiment.
It's an experiment. So it's random assignment.
So we ran the assignment, which means you don't need 10%.
Correct. Yep.
Okay.
What was the population? So,
So it's not all streams. You only tested one stream. So the population would be the stream, like everywhere along that stream that you tested. But it would just be that one stream. It's not like all streams across the world because you only pulled your samples from that one stream.
And how come? So because it's less than 30, you had to have drawn a picture showing that it was an escape.
Yes, you don't have your like little skewness, no outliers in your sample. So you would need a picture of that to show me that.
Okay. I just said it's just like cat food is like random. I don't know if they like.
I didn't take off any points for that. You said assumed and I gave you that, but you still need to like talk about like what was it that gave the randomness here?
The cat food in or
Look up here. Why is there randomness happening?
oh, he flips his coin to the side.
There you go. He's doing random assignment with a coin flip. So is he doing sampling here?
Is he doing it?
Is he doing sampling?
No.
No, he's doing
Random.
random assignment, so that would make it what kind of situation? Starts with an E.
I don't know.
Doing an experiment.
Oh, yeah. And then like here, I just have to write P or M1 minus M2.
If you define exactly what mu1 and mu2 are, so somewhere in here, if you said mu1 is pick a pear, mu2 is pickled peppers, yes. Otherwise, down here you would say pick a pear minus pickled peppers. You have to show me that direction there. All right, on the check your understanding, your parameter. You do have to say what parameter you are using here, whether it is P for proportion or mu for mean. It's not enough to just say parameter, because there are many things that are parameters. The statistic in this case, we have X bar, 46.4. We have the sample standard deviation of 18.8. I'm also going to write down my N value since I'm going to need to use that. Alpha level they gave us as 0.01. And then our hypotheses, mu is equal to 51, mu is less than 51.
Yeah. This is saying like we used a 99 and now we're using 95. Right?
Yes.
That's what it was.
Name of the procedure here, one sample t-test for mu. Our conditions, we have the random condition. It says a random sample of 75, so we've got that one. That's so we can generalize to the population of all US drivers. We have our 10% condition. 75 is less than or equal to 1/10 of all US drivers. That is definitely true. That allows me to sample without replacement, so I get independence. And then we have normality. 75 is greater than 30, so I have the central limit theorem. It's not just enough to say 75 is greater than 30. You've got to tell me that that means you can use central limit theorem there. And that means that the sampling distribution of X bar would be approximately normal. Anytime we are doing significance testing, our general formula, standardized test statistic equals statistic minus parameter divided by our standard deviation. And I can come back to this if you guys need me to, but I want to finish out going over this real quick. So specific formula, T equals X bar minus mu over Sx divided by N. So I got a t-score of negative 2.119. Drew my picture. You do have to label it so they know whether it's a normal curve or a t-distribution. T, and then you label it with the degrees of freedom. So T74. We have our test statistic, which gives us, we use to find our p-value of 0.0187. Since they had us use an alpha level of 0.01, we failed to reject the null. At an alpha level of 0.05, we would reject it, but at 0.01, we fail to reject.